Well, welcome to the quantum uncertainty principle, our final act. In this final video, we're going to talk about Pauli matrices as representations of the XYZ apparatus that we have been talking about. We'll try and derive two Pauli matrices, and using those two matrices, we'll derive the third one. We'll then establish the commutation relation between these matrices, and then using what is called the Cauchy-Schwarz inequality, we're going to combine all of this together to derive the uncertainty principle. So let's get started. Now we have already introduced a matrix, a 2 by 2 matrix representing the Z apparatus in the basis, where our basis vectors are spin up along the Z direction and spin down along the Z direction. And it turns out that the Z matrix is sometimes called sigma Z matrix, is one example or one of the Pauli matrices. And it turns out to be a diagonal matrix with entries 1 and -1 along the diagonal and 0 along the off diagonal. Now, how do we represent the X apparatus while retaining our basis as the spin up along the Z direction and spin down along the Z direction? Now, essentially what this means is that we require another 2 by 2 matrix which has as its eigenstates or eigenvectors the plus x quantum state and the minus x quantum state. That is a quantum state pointing along the positive x direction, which we have already represented using a column vector with entries 1 over root 2 and 1 over root 2. And the other eigenstate is a minus x quantum state, which has entries 1 by root 2 and -1 by root 2. So given this information, let's assume that the matrix we're looking for, the X matrix that we're looking for, is again a 2 by 2 matrix with entries A, B, C, D. And if we solve the eigenvalue equations, we find that the simplest representation for this X matrix is a matrix with zeros on the diagonal and 1 along the off diagonal. And you can quickly check this through a calculation that indeed this matrix has two eigenvectors, 1 over root 2, 1 over root 2, that's the first column vector, the first eigenvector, and the other eigenvector is 1 over root 2 and -1 over root 2 along the column. And these two eigenvectors have eigenvalues +1 and -1 respectively. Alright, so we have two of the Pauli matrices with us, sigma x, which we can think of as representing the X apparatus in the simulation that we've been doing so far, and sigma z. Now I'm going to tell you a shorthand way of figuring out the third Pauli matrix, which will also give us another interesting insight into the nature of how these Pauli matrices interact with each other in some ways. So let's do one thing. Let's find out the product of sigma z with sigma x in the order that I'm going to I'm going to write sigma z first and multiply that matrix with sigma x, and then I'm going to invert this order and I'm going to compute the product of sigma x times sigma z. Now, if you're not familiar with matrix multiplication or not seen the kind of interesting aspects that can come out sometimes, you'll quickly realize that the order in which we multiply these 2 by 2 matrices actually matters and gives us different results. For instance, sigma z times sigma x is not equal to sigma x times sigma z. And if you do this calculation and try and find out what is the residue, in other words, what is it that you get if I have sigma z sigma x minus sigma x sigma z, you'll see that if you do the calculation, you'll see as written in the third bullet point here, we end up with a matrix which has a value of 1 and -1 along the off diagonal and 0 along the diagonal up to a scaling factor of 2. It turns out that this third matrix, if I do a bit of some bit of manipulation with it and multiply the entries of the matrix with I, or rather with -I, we find that we can discover the Y matrix, or rather the matrix representation of the Y apparatus, which we denote by sigma y. And I leave this as a quick exercise for you to compute the eigenstates, the two eigenvectors associated with this sigma y matrix. It will turn out that these will represent the plus y and minus y quantum states respectively. I'm going to build on this idea a little further, but this idea of computing the product of two matrices, let's say in this case sigma z, sigma x, and then inverting the order of the matrices, that is computing sigma x and sigma z, and taking their difference is what we call the commutation of two matrices. More on this in the next slide. So we now have the three Pauli matrices with us, sigma x, sigma z, and sigma y. And the reason we did a bit of a manipulation and define sigma y the way we did was because if I now take these three matrices and let's say square them one by one, we find that all of them square to the identity matrix. Even more interestingly, pairs of these matrices satisfy an interesting commutation relationship. That is, if I take sigma x, sigma y and subtract from it the product sigma y, sigma x, I end up finding 2 times I times sigma z, where I is the unit imaginary number. Likewise, if I move cyclically in the order x, y, z and now compute sigma y, sigma z and subtract from that sigma z times sigma y, I end up finding 2 times I times sigma x. And for the third relationship, we find sigma z times sigma x minus sigma x times sigma z is equal to 2i sigma y, which is how we ended up introducing the sigma y matrix in the first place. So this symmetry in the way these three matrices interact with each other was one of the motivations why we defined sigma y the way we did. But if you do the calculation, you also find that the eigenstates of sigma y correspond to the plus y and the minus y eigenstates. Now this gives us a good opportunity to define what is called the commutation relationship of two matrices or two operators. We define the commutation of two matrices AB as the product A times B minus B times A. Now for matrices which have this commutation as non-zero, which means that if the order of the multiplication of matrices gives us different results, if we change the order of multiplying the matrices, we end up obtaining different results, then the commutation of these matrices will be non-zero. Now there are classes of matrices for which this order of multiplication does not affect the outcome. For those matrices, the commutation will evaluate to 0. But for those for which the commutation of the two matrices is non-zero, we call such pairs of matrices as non-commuting matrices. And in the context of quantum mechanics, we call them non-commuting observables. Such non-commuting observables are one of the key ingredients in deriving the uncertainty principle and in explaining the outcomes of the kind of experiment we introduced in the first few videos of this particular series of videos on the uncertainty principle. So we'll delve a little bit more deeper into this aspect in the next couple of slides. Now using the triangle inequality for vectors, we can derive another interesting feature or property of two vectors in a vector space, and this is called the Cauchy-Schwarz inequality. Now we know from the triangle inequality that given two vectors x comma y, the modulus of x plus the modulus of y, by modulus we mean the length of the vector x plus the length of the vector y, is greater than equal to the length of the vector joining the two vectors x and y, which is, in other words, it's greater than equal to the modulus of x plus y. Now I can write the triangle inequality using the bracket notation by expressing the modulus of a vector via the square root of the inner product of a vector with itself. And using the bracket notation, that means taking the brow of x and multiplying it by the ket x and then taking the square root of that. And this gives us the length of vector x. So if I write the triangle inequality using the bracket notation and I square both sides, I can obtain the Cauchy-Schwarz inequality expressed here again in the bracket notation. And the reason I'm using the bracket notation is because it'll come in handy when we derive the uncertainty principle later on. Now the Cauchy-Schwarz inequality, essentially what it says is that the length of a vector, let's say x times the length of the vector y, is greater than equal to the square of the length, or rather the projection of x along y. So if I take the projection of x along y, which is if I take the bra of x and multiply it by the ket y and then take the norm of this and square it, what I obtain is the projection of x along y squared, and this is less than equal to the length of x times the length of y. I'm going to use this idea along with the commutation relationship to derive the uncertainty principle in the next slide. But I just want to make one more point here, which is if you notice the right hand side of the third bullet point where we've expressed the Cauchy-Schwarz inequality, I've explicitly made a slight careful note of the fact that when we are dealing with complex vector spaces, as is the case for us, the bra of x times ket y is different, is not the same as bra of y times ket of x. So when we square the right hand side of what is written in bullet point 2, we do not mix up bra x times bra ket y with bra y times ket x. So therefore I've written this not as 2 times bra x times ket y, but I've written this as bra x ket y plus bra y ket x. So I hope this point becomes somewhat clear if you refresh the bracket notation which we have introduced in one of the previous videos. The bracket notation also comes in particularly handy when we want to express the mean, the variance, and other such statistical measurables of any measurements we perform in quantum mechanics. Associated with measurements, we obviously have operators. So let's say I want to express the mean value of an operator on an observable B. Now, if you look at the second last bullet point written in blue color, you'll see that the mean value of an operator B given a state psi can be expressed in the form bra psi B, the matrix representing operator B, times ket psi. And the way we calculate, or the way we obtain this calculation is we can express psi as a column vector. B is a matrix, so when I take the matrix and multiply it by the column vector, I get another column vector, and then we just multiply this column vector with the bra associated with psi, and that gives us the mean value of the observable B, given that we begin with the state psi. Now what does it mean experimentally? It means that B could perhaps be some kind of an apparatus, and then psi, we prepare many quantum states, all of them initially in the state psi, and when we pass these quantum states through the apparatus, at the output of the apparatus, when we perform the measurements, we'll see that the average or the mean value of our measurement is given by the expression psi bra psi B times ket psi. And you can go through this calculation to see how this derivation really comes about. And if you have any questions, feel free to comment or write me a message through the website. In the same way, we can express the variance associated with an observable B, and in this case, all we have to do is take bra psi, multiply it by the matrix representation of the operator B, and when you subtract the expectation value of B from the operator, just like we define variance in the usual sense, and then multiply this with the ket. Now we're going to use this notation, or this way of calculating the mean and the variance of operators to derive the uncertainty principle in the next slide. So let us consider two observables, Hermitian matrices for us, A, B. And let's say we have an initial quantum state psi. Now we're going to do a bit of algebra just to get to the uncertainty principle. And we're going to use two main ingredients, non-commuting observables and the Cauchy-Schwarz inequality. So we have A, B as our two observables, and let's define two new quantum states, ket x, which is A minus the expectation value of the observable A in the state psi, and I'm going to define A minus the expectation value of A as operating on the initial state psi to give us the new ket x. Likewise, let's define get y as I times b minus the expectation value of b as it operates on the initial get psi. Now remember, these expectations values a, the expectation value of a and expectation value of b are computed for the initial state psi. Now using these two very simple sort of redefinitions of the quantum state, we're going to define the inner product of x with itself, and if I perform this calculation, you'll see that this, as noted in the second bullet point, this gives us the variance of the observable A in the state psi. And for a quick refresher of how the mean and the variance are defined, please refer back to the slide we just talked about a couple of minutes ago. Likewise, if I take the inner product of the get y with its corresponding bra, we end up obtaining the variance of B, and that's all we need. All we now do is plug in the inner product of x with itself and the inner product of y with itself into the Cauchy-Schwarz inequality, and on the right hand side, when we simplify the right hand side with the definitions for the get x and get y respectively, we discover or we derive for ourselves what's called the uncertainty principle. And what it says is that 4 times the variance, 4 is just a scaling factor in this case, 4 times the variance of the observable A times the variance in the observable B is greater than equal to the expectation value, or rather mod of the expectation value of the commutation of A comma B. In the next slide, we're going to use this uncertainty principle back. We're going to go back and use this to Pauli matrices which we have introduced, which will help us explain some of the findings of the simulations that we have been doing so far. Now the uncertainty principle, the way I wrote it in the previous slide, we can just take the square root of that expression and rewrite it or express it in the form of 2 times the standard deviation in the observable A times the standard deviation for the observable B is greater than equal to the square root of the expectation value of the commutator of AB in the state psi. Now let's, as an example, let's say the observable A for us is the Pauli X matrix or sigma X. Likewise, let's say the observable B is the Pauli Y matrix sigma Y. Then we know from the relationship between these Pauli matrices that the commutator of A comma B, or rather of sigma X comma sigma Y, is nothing but 2I times sigma Z, which is the Z Pauli matrix, or rather a representation, if you want to think of this experimentally, a representation of the Z apparatus that we have been talking about so far. If I go back and plug this into the version of the uncertainty principle written in the first bullet point here, we find that the variance in sigma X times the variance in sigma Y is greater than equal to 1 over square root times the expectation value of the observable sigma Z. This uncertainty relationship has very interesting consequences. Now let's go back to the experiment that we've been talking about. Let's say we have a collection of particles, quantum particles, and we pass all of them through the Z apparatus, thereby preparing them in one or the other Z state. And let's say for simplicity we have prepared all of them, we just look at the ones that move up along the Z apparatus and therefore they have a spin value of +1, and we only retain these particular quantum particles. So we've prepared our quantum particles in the state which has a spin up along the Z direction. Now what this means is that the expectation value of sigma Z, if I perform another measurement of these quantum particles, we know that all of them will give us a value of +1, which means their expectation value is +1, which means the expectation value is non-zero. Now if I go back and plug this into the uncertainty relationship, what this tells me is that the left hand side, which is the standard deviation of an observation of the X value of the spin times the standard deviation of the observations of Y value of the spin should be greater than equal to something non-zero. What this means is that the standard deviation, or if you want to think of it in terms of variances, variance in the values of the x value of the spin cannot be 0, because if it were 0, the uncertainty principle will be violated. Likewise, variances in the value of sigma y, or the y component of the spin, cannot also be 0, and that's because the right hand side is non-zero, which means that a subsequent measurement, so let's say we have prepared our quantum state in, say, spin up along the z direction. Now subsequent measurements along the x apparatus or the y apparatus is bound to give me an uncertain or a random result, because if the standard deviation of a variable is non-zero, it means it's a random variable, and that is really the heart of the uncertainty principle. In very terse language, what this means is that the measurement of the x apparatus or the y apparatus cannot be determined with certainty if we know that the state has a specific z value. And likewise, for any pair of non-commuting variables, if I prepare them in one of the if I prepared them along one of the directions, then a subsequent measurement along a non-commuting sort of direction is bound to give me results which are uncertain. Or in other words, a measurement via one of the apparatus is bound to modify subsequent measurements via any of the other non-commuting observables. This idea lies at the heart of the uncertainty relationship, and in fact there are many such pairs of observables or variables in quantum mechanics whose values cannot be simultaneously determined with certainty. Position and momentum being very famous pairs of such variables which also satisfy a version of this uncertainty relationship. So I hope this series of videos was useful and gave you a glimpse of the uncertainty principle and sort of all the mathematics that goes into deriving it. Hope to continue discussing many more such ideas with you. Stay tuned, keep commenting and letting us know what content you want from us. Hope to catch you soon. Thanks for watching.